Here's a reaction where we've got methane and ammonia making hydrogen gas and hydrogen cyanide, toxic substance. Now, all of the atoms work out. One carbon, 4 plus 3, 7 hydrogens, 6 plus 1, 7 hydrogens, and 1 nitrogen and 1 nitrogen. It's a balanced reaction. That's pretty well set. But what we don't know is about the heat of this reaction, the energy part, which is just as real as the atoms, because there's going to be a change in energy. Now, there are 3 ways to find the change in energy for a reaction. One is to physically do it in a calorimeter, measure the change in temperature, masses, specific heat, and you can get the joules. You'll find out energy going in, energy going out. Another is to have an enthalpy of formation table and use those values, products minus reactants. And the third method, which we're going to deal with here, is adding reactions. So here we've got this reaction, and the energy part's missing. And that's critical for a reaction. In fact, the energy part tells us if this reaction may actually occur, and if it does occur, to what extent it does. So it's an important part of what's occurring here. In this case, this is not a reaction you want to do in a calorimeter. I mean, you're making this poisonous gas. No, stay away from it. Instead, you could use the enthalpy formation tables, but in this reaction, you want to focus on the third way that you'll see used on the AP exam. In fact, if you don't use it on the AP exam, you must have skipped the question. So let's find out this technique. Here's the question. Find the heat of reaction using the following thermochemical equations. So we're given 3 equations. We're told how much energy is released or absorbed in it. We know the atoms and we know the joules. 2 important things in the changes. Now, you can be assured when they give you the equations, you'll be able to use these equations to get the answer. So you know these equations are going to help you. So what are we going to do? Well, look at the equation here that we want. This is what you focus on first. I've got methane. Well, which of these reactions has methane in it? Here, this one does. Reaction 2. Fine. We'll use that reaction, and we'll use it to build this new one. Not the new one, the original reaction. Now, I've written that equation down already. Here it is, but you'll notice I reversed it. I put the methane, which is a product here, as a reactant over here, because my desired equation has methane as a reactant. And you can flip an equation around. See, I just did it. Now, that means this enthalpy here is going to be wrong. It's not going to be 74.9 kilojoules for this mole. When you flip a reaction around, you have to change the sign of the reaction, because that makes sense. You know the rule. Let me just get rid of that, because that's wrong. There. When this reaction occurs, when methane is made, it's exothermic. Heat's released. Joules get sent into the outside. Joules that were in this graphite and hydrogen. Well, if we're going to make the graphite and hydrogen back again from the methane, we've got to dump that heat back in. So this changes from an exothermic reaction to an endothermic reaction, and here it is. I've got it written in red. The products have got weaker bonds than the reactants. We've put that energy in there. That energy is now back in when we unmake the methane and get our graphite back again. So, hey, this is taken care of. Again, we're going to recreate this reaction. Ammonia. We need ammonia next. Okay, ammonia's got to be in one of these equations, and here it is. Okay, same old. The reaction is backwards, so I just write it the correct way. And we know that this heat is going to have its sign changed from negative to plus. But there is also a twist. This is the second twist you find. There's a 2 here, and we only need 1 ammonia. Well, that's going to be pretty obvious. If I want 1 ammonia, divide everything by 2. I'll divide this by 2. That gives me 1 ammonia. Get rid of that 2. Now, dividing this nitrogen by 2, the best way is just to say, okay, I got 1. Now I got a half. And then here for the hydrogen, we have 3 of them, but change it to grab my red 3.5 and put it right in front. So I reversed and divided by 2. So grab my calculator and bring it up here. You probably don't need this. Your math is going to be good enough. This is our ammonia. It's our now positive 91.8. Let me get my, as you can see the whole thing. 90, you don't see the 1, but you can see it up there on the screen, divided by 2. Okay, now, there you 45.9. Oh yeah, that makes sense. But let me get it going here and pick up my new, I guess you could call it new enthalpy. For this new reaction, I have to dump in 45.9, half of this, to make half as much material. Now, let's go to the next part. We've got the reactants taken care of. Good. Reactants are taken care of. Let's make sure we've got our products. Well, we have to make hydrogen. And I look around and I say, uh-oh, hydrogen all over the place. Which one of these equations do I deal with? None of them. If you have a substance in your desired reaction that's scattered around, ignore it for right now. It'll work out later. Save that for last. In fact, you don't even have to do that, because if you get the HCN taken care of, everything else will fall into place. So I'm going to try and find something with my cyanide, HCN, hydrogen cyanide, a weak acid. And here it is. And goodness, I don't have to reverse it. That's nice. Makes things a little bit easier. Here it is. Here it is. The same equation. But I only need one cyanide. So, okay, here we go. We got to do our division by 2 again. And I'll get my little eraser here. Divide by 2. Come on. Grab that. It's being stubborn right now. Okay, good. Erase. And I'll take this half, copy it, and put it in front of that nitrogen. Right there. There's that half of N2. I can get rid of my carbon. In fact, actually, I'm going to have to use that half again. So I'll put that right in front of my hydrogens. Right there. And then my graphite, that's divided by 2. Erase that too. Good. Oh, okay. Here we go. We've got to get rid of this, because if I change the reaction, I've got to change the heat. And that's going to be our 135.2. I won't bring up the calculator. Save us some time. You can do it yourself if you like. We didn't have to change the sign. We just had to divide by 2. I rounded it to 135.2. And we're set. So right now, I've taken care of the methane, the ammonia, the hydrogen cyanide. And I said the hydrogen will take care of itself. So what I would do if I was in a rush on an exam, I would now take these 3 equations, these 3 heats, add them together, and be confident that that's going to be the heat for this reaction. You know, if I add these up, I get 257.0 kilojoules per mole of reaction. And go on to do some other stuff. If you're careful doing all of this, remember to divide and change the enthalpies. Don't forget that last step to change the enthalpies. It's going to work out. So if you're confident on that, and you do a little juggling here, you're set. You can leave the video, save yourself some time. If you really want to see how this works out and how it all adds up, here we got a couple of minutes. Let's do it. A methane, exactly where we want. Fine. We've got our methane. But we got graphite. Well, that's easy enough to get rid of, because there's graphite as a reactant, graphite as a product, and you know, if they're on opposite sides of the equation, you can cancel. Oh, love algebra. You get a chance to use your algebra in chemistry all the time. So there's our graphite. Hey, things are simplifying already. Now I've got 2 hydrogens here. I need 3 of them. Now let me see. I've got a hydrogen over here, a 1/2, canceling out one of these 3 halves. So when this cancels out, this 1/2, I'm trying to get rid of on this side of the equation, it makes this 2 halves, which means it's just 1 hydrogen. So 2 plus 1. Oh, there's our 3 hydrogens. Didn't I say they would work out? Didn't I tell you it's going to, if you get the others, the last part will come in. Now, I've got a half of a nitrogen over here. that weird 1/2 of an N2 mole, and I have a half of nitrogen here. And look, it adds up. I've got methane and ammonia making 1 hydrogen cyanide. Here we go, 3 hydrogens. Now that took some extra time, but at least you understand what's happening here. The 3 equations, A, B, and C, helped us figure out this equation. This is going to be an endothermic reaction. We have to dump in 257 kilojoules to make 1 mole of hydrogen cyanide and 3 moles of hydrogen from 1 mole of methane and ammonia. And that's it. Balancing reactions can take some time. But remember, you really don't have to go through this last step if you were careful on these first 3. In fact, you can sort of imagine yourself saying, oh, I got to make a methane. Okay, here's a methane. Change the sign. I've got to have an ammonia. Change the sign because it's a product here. Divide by 2. And I need 1 cyanide. Divide by 2 and add them all together. So you can do it fast if you've got faith and can spot this stuff. So practice with these and get good at them. And then when you take the AP exam, you'll be all set. And also, if you're trying to find the heat of a reaction someday, you can use this system too. It's beautiful.